All right, let's do a full lesson and a little bit of practice on L'Hopital's rule. I know we did an impromptu lesson a few weeks ago, but I just want to make sure that we hammer this concept home because I can guarantee you will use this on the AP test. All right. So we talked a little bit about indeterminate form when we did this lesson before. Okay, there are actually 7 indeterminate forms, and they're all right here. Okay, so write these down on your note sheet. We have 0 over 0, infinity over infinity, 0 times infinity, 1 to the infinity power, 0 to the 0 power, infinity minus infinity, and infinity to the 0 power. The 2 that we really care about, though, are these first 2, 0 over 0 and infinity over infinity. So, as we've said before, okay, we're going to take the limit of a quotient, and these are the types of problems that we usually see, right? Some function divided by some other function. So L'Hopital's rule states that when I plug in that initial value, okay, so when I plug in whatever value is right here, and I get 0 over 0 or infinity over infinity, then what I can do is just take the derivative of the top and the derivative of the bottom. Now, make sure that you understand this is different than the quotient rule, okay? So, this is what you should write down in your notes, okay? This is L'Hopital's rule. If when we plug in that value we get 0 over 0 or infinity over infinity, we can just take the derivative of the top and the derivative of the bottom, and then that's our answer as long as that limit exists, okay, or is infinite. We could get infinity or negative infinity as an answer when we do this. All right, so let's go ahead and try some examples here. All right, on this first example, remember the very first thing we have to do is plug in the value, no matter what our limit question is. That's true of any limit, okay? Plug in the value first. So if I plug 5 into the numerator, I'll get 2 times 5 squared, so that would be 50, minus 45 minus 5, that would be 0. And then in the denominator, I would get 5 minus 5, which is 0. So I get 0 over 0. So what I can do is take the derivative of the top and the derivative of the bottom. So I can say this is the limit as x approaches 5 of 4x minus 9 over 1, right? So now let's try to plug 5 in again. Now I can, right? I will get a number. So this would just be 4 times 5 minus 9. So 20 minus 9 would get me 11. All right, now one small thing that we need to make sure we're paying attention to. Notice how I wrote limit as x approaches 5 again in my second line. Okay, when we're taking the derivative, we still have to write limit. Okay, we can't get rid of writing limit until we're actually plugging in a value. Okay, so that's just a small nitpicky thing that they would nail you for on the AP test. All right. So I want you guys to go ahead and try this second example then. All right, so first, again, we have to try to plug in our value. So if I plug negative 5 into the numerator, I would have the square root of 4 minus negative 5. So that would be the square root of 9, which is 3, minus 3. Obviously, that's 0. Denominator, negative 5 plus 5 is 0. So we can use L'Hopital's rule. So let's plug in negative 5, let's find the derivative first. So this will be the limit as x approaches negative 5 of, now remember, whenever we have a square root, right, this is just the same as 4 minus x to the 1/2 power minus 3. I didn't take the derivative, I just rewrote that. So now if I want to take the derivative, I would say this is 1/2 times 4 minus x to the negative 1/2 power, then times the derivative of the inside, so that would be negative 1, right? And then that's all over 1. So now we can try to plug in negative 5. All right. So I can say this is equal to 1/2 times 4 minus negative 5 to the negative 1/2 power times negative 1. So this becomes 1/2 times 9 to the negative 1/2 power, and I'll just go ahead and throw that negative sign out front for negative 1. Now what does 9 to the negative 1/2 power mean? Well, that negative 1/2 power, I could take this to the denominator and say this is 1 over 9 to the positive 1/2 power. Well, positive 1/2 power is just the same as a square root, right? So this is just negative 1/2 times 1/3, which would get me negative 1/6. All right, so my answer is negative 1/6. All right, now here, all right, we can use L'Hopital's rule multiple times in a row, and we'll see that would apply to this problem. So if I plug in negative infinity here, I would get negative infinity squared over e to the infinity. So I would get infinity over infinity, right? So we can use L'Hopital's rule. So if I take the derivative of the top and the bottom, this becomes the limit as x approaches negative infinity of 2x over e to the negative x times the derivative of the exponent, which would be negative 1. So if I plug in negative infinity, I would get negative infinity over negative infinity, or infinity over infinity. What that means is I can use L'Hopital's rule again. I can just take the derivative of the top and the bottom again. So the derivative of the top now is 2. Derivative of the bottom would be e to the negative x times negative 1 times negative 1, so it would actually be positive e to the negative x. Well, now I can plug in negative infinity, and if I do that, I end up getting 2 over e to the infinity. All right, and remember, any number over infinity, which that would be the case here, right? A number over infinity we say is just equal to 0. All right, so you guys then try example 4, and here, okay, I'll tell you before you try it that this is one where we will have to use L'Hopital's rule multiple times. So give this one a try. All right, so if we plug in negative 2, okay, I'm not going to write out the whole calculation here, but if we plug in negative 2, we will get 0 over 0. So we can take the derivative of both the top and the bottom, and we would get 3x squared plus 2x minus 8 over 3x squared plus 16x plus 20. So now, if I plug in negative 2, we actually end up getting 0 over 0 again. So I can plug in, or I can find the derivative of the top and the bottom again. So we would get 6x plus 2 over 6x plus 16. All right, so let's try to plug in negative 2 now. So I would have 6 times negative 2 plus 2 over 6 times negative 2 plus 16. So that would get me negative 10 over 4, which would be negative 5 over 2. All right, let's try another example, right? Trigonometry and transcendental functions. Transcendental functions just means logs and exponentials. So here, okay, this one we're going to use a different strategy, an interesting strategy to start off here. I realize this strategy that I'm going to show you here is not something that you would think of right off the bat, okay? But hopefully seeing me do it here, okay, might allow you to think of it in the future. If you remember way back when we talked about properties of limits, I can actually split a limit up into the product of two separate functions. What that means in terms of this problem, I can say, that this fraction, I can split this up into the sine of x over x times 1 minus the cosine of x over x. Right? I'm just splitting up that denominator into x times x. So I can say this is the limit as x approaches 0 of sine of x over x. Oops, I got some dots down here. Times the limit as x approaches 0 of 1 minus cosine of x over x. Okay, all I did was split up that fraction, right? And I can do that. I'm allowed to split up a fraction like that if I'm multiplying. So now it's going to be much, much easier to take the limit of each of these pieces and then multiply those pieces together. So in the first piece, right, if I plug in 0, I get 0 over 0. Sine of 0 is 0. In the second piece, cosine of 0 is 1, so 1 minus 1 is 0 over 0. So I can use L'Hopital's rule on both of these pieces. So I can say this is the limit as x approaches 0 of the derivative of sine is cosine, so cosine of x over 1 times the limit as x approaches 0 of, so the derivative of 1 minus cosine would just be sine over 1. So now let's plug in 0. So the cosine of 0 is 1, right? So this would end up just being 1 here, times the sine of 0 is 0. So this second piece would equal 0. So the entire answer then is 1 times 0, which is 0. Okay? So this strategy, right, if I look at my original function, okay, and I see I could use L'Hopital's rule, I get 0 over 0, but I would have to use product rule. I would actually have to use L'Hopital's rule twice because I would get 2x in the denominator, then I would have to take another derivative. This strategy avoided all of that, right? If I just split this up into two fractions that I was multiplying together, right? So in this second example, you do not need to use this strategy of splitting up fractions, right? This is just an example where we've got logs and exponentials. So give this one a try here. All right, so again, first thing we have to do is plug in this value. So if I plug in 1, the natural log of 1 is 0. So I get 0 minus 1 plus 1. Well, that's 0. And in the denominator, I would get e to the first minus e, which would be 0. So I can use L'Hopital's rule. So I can say this will be the limit as x approaches 1 of, so the derivative of the numerator, derivative of natural log of x is 1 over x. Derivative of x would be 1, so I get 1 minus x, or 1 over x minus 1 over the derivative of e to the x is e to the x, and the derivative of e is 0 because that's just a number. So I can plug in my value of 1 here. So this would end up being 1 over 1 minus 1 over e to the first. So I get 1 minus 1 in the numerator, which is 0, divided by some value is 0. All right? 2 more. So here, okay, we have limits as we're approaching infinity. So on this one, if I plug in infinity, we can very clearly see that we'll get a bunch of infinities in the numerator and an infinity in the denominator. That means that I'll get infinity over infinity, so I can use L'Hopital's rule. So this would be the limit as x approaches infinity of 9x squared plus 10x minus 3 over 12x squared. But again, if I plug in infinity, I'll get infinity over infinity. So let's do it again. So limit as x approaches infinity of 18x plus 10 over 24x. But again, if I plug in infinity, I'll get infinity over infinity. So let's try it one more time. So I can say the limit as x approaches infinity, and this would actually end up being just 18 over 24. All right, if I take those derivatives, well, there are no more x's, all right? So there's no place for me to plug in infinity. I actually have a value, so that's my answer. All right, 18 over 24 would reduce to 3/4. So that's my answer here. All right, so I want you guys to take a look at the last example and give this one a try. All right, so if we plug in infinity, we can clearly see that we'll get infinity over infinity. We'll have x's in both the numerator and denominator that would be infinity. So let's take the derivative of both. So we can say limit as x approaches infinity of 8x minus 3 over e to the 2x times 2, right, times the derivative of the numerator plus 1 over x. All right, well, if I plug in infinity, again, I will get infinity over infinity. So let's take the derivative again. So we will get limit as x approaches infinity of 8 over e to the 2x times 2 again. So I'm going to go ahead and write that just as 4 times e to the 2x. Now, 1 over x, remember, is just x to the negative first. So let me just, so this is x to the negative first. So if I take that derivative, all right, derivative of x to the negative first is negative x to the negative second, which we know is the same as 1 over x squared. All right, so I can actually just write this as minus 1 over x squared. Now, if we plug in infinity, we will get 8 over some really large number minus 0, right? So 8 over infinity, any number over infinity is just equal to 0, all right? So go ahead and try the practice problems now.